All right, welcome back, ladies and gentlemen. I'm going to try to keep this one straight to the point so that it isn't so long. This is a projectile motion problem, an example. And this one is going to be a horizontal launch, and we are given the initial launch vector. So here is our problem. A middle schooler kicks a ball too hard and it rolls off of a cliff with an initial velocity of 6 meters per second. If the cliff is 700 meters high, what is the range of the ball? Because that's exactly what we do, is we put middle schoolers on a field where they can kick balls around. That is above a 700 meter high cliff. Anyway, range is what it's looking for. And we need to make sure we understand this word. This is a nice, cool word for the horizontal displacement, delta x. And so that's what we're looking for. That's a quantity in the horizontal or x direction, and we know this is going to be a horizontal launch. So I'm going to share with you guys, I'm going to work through this problem using a paper that you should have with you as well. I'm going to give you guys a bunch of copies of these sort of problem-solving templates. And so I'm just going to go through the various places and spaces on this paper, and we'll see what we come out with at the end. So we got to draw it first of all. And no, I'm not rewriting the problem. The problem's written down. Okay, you can pause the video, pause, and you can see it anytime you need to. I need to sketch it. I need to draw it out. So this is clearly horizontal launch off of a cliff. And so I'm sketching a cliff. Super simple. This is like my stick figure cliff. All right, and the ball is at the top of the cliff to begin with. This middle schooler gives it a horizontal velocity, so right off the cliff horizontally, but of course it doesn't fly out horizontally, and it does a thing like that. Now, since we're looking for the delta x, the range, I'm going to go ahead and label that. I'll put it right here. Delta x is more or less. The ball doesn't become a projectile until it leaves the cliff edge, right? So I can measure delta x from the cliff edge to where it lands. There we go. There's my delta x, that whole distance right there. I do know also that the cliff itself is 700 meters high. But if I'm measuring the right direction, if I think of that distance as the distance down to the bottom, I need to be really smart with this. Let me see, let me get that in frame a little better there for you. Well, look, it's downward. I haven't yet applied a coordinate system, but I really should. There's y. There's x. That's supposed to be a y. There we go. Look at this. This 700 meters, as soon as I do that, that's not positive 700. It's negative. Okay. Oh, and I could label that arrow right there. That's the initial velocity. For a horizontal launch, what's the launch angle? The initial launch angle is 0 degrees from positive x, right? That's an equal sign. Cool. That's pretty good for a sketch. That's a sufficient, right? Okay. I want to resolve the initial launch vector into its x and y components. Oh my goodness. Well, we have this vector, vi, and we were told that was 6 meters per second. Okay, cool. We have a coordinate system, x and y, and so what is Vx initial, the x component? Well, how much of that vector is in the x direction? All of it. So don't have to do any math on that one. No trig on that one. Vy initially, the velocity in the y direction initially. How much of that vector is in the y direction? None of it. So that was easy. Okay, I've got the two components in the x and y direction of that initial velocity. Awesome. I'm going to come over here and I'm going to list some x and y information. What do I know? Well, I don't know the displacement, the range. In fact, that's the thing this question wanted me to find. Velocity in the x direction. Well, I know the initial velocity in the x direction. Is that what this wants here? If I remember one of the cool facts about projectile motion and it's parabolic and all those other things, one of those cool facts was that the initial velocity in the x direction equals the final velocity in the x direction, because it doesn't change, because it's constant motion in the x direction. So that's a 6 right there. That is 6 meters per second. Cool. Acceleration in the x direction is 0 meters per second squared. Awesome. Time, I don't know the time yet. And I'm probably, since that's the range, this thing right here is the range. That's what I'm looking for. That's a quantity in the x direction. I'm going to have to do a calculation with stuff in the x direction. But going to need the time. I guarantee you, going to need the time. Well, cool thing. There's another cool fact about projectile motion, and that the time in the x direction equals the time in the y direction. I know there's no delta in front of that. If that bothers you, just draw it in. Oh my goodness. Okay, so let's see what else I can fill in over here, because I don't know that. Maybe I'll use the stuff in the y direction to find the time, write that answer here, and then use that to work this out. You'll see that coming. So displacement in the y direction. Remember how I wrote that as a negative value? It's headed in which direction? The positive y direction? No, it's down, so it's negative 700. I know that number. Negative 700 meters. Okay, cool. Initial velocity in the y direction. Aha, got it. 0. Okay. Acceleration in the y direction. Here's a cool fact about projectile motion. That's always negative g. We put a minus sign in front of sweet baby g, so negative 9.8 meters per second squared. Okay. Right on. Equations. Now, I've got these boxes for listing equations. This is straight out of your notes, and I am going to ask you to do that. When we work on this template, in fact, this is probably going to be an assignment at least once, maybe twice. Fill these in straight out of your notes. So what are the equations for the x or horizontal direction? Well, this isn't so much an equation, but it is a fact, and I've already got that fact written up here. The acceleration in the x direction is 0 meters per second squared. That's an m. I promise. What else do I have in the x direction? One of the cool facts. The Vx initial equals the Vx final, because it's constant motion. That is an equation, and there's one more. And in fact, it's the equation for the range, for the displacement in the x direction. Vx times delta t. Okay, there we go. Now, that'd be cool. Like if I knew that Vx, I do. And if I knew that delta t, I don't. Well, then if I knew it, I could find that right away. I don't seem to have enough information in the x direction. We'll get to that. Equations in the y direction. Look them up. You know what they are. They're in your notes. Well, should I put them in here? I'll put them in here. I just want to make sure I'm going to have enough room, because these get a little bit busy with some symbols. I'm not going to rewrite the equation one, or I'm sorry, the acceleration one. I'm going to go right to the others. We have velocity y final equals velocity y initial plus acceleration in the y direction times delta t. Okay, then the second one, I'm going to write 3. Second one is displacement in the y direction equals the initial velocity in the y direction times delta t. Let's see if I can squeeze it all in here. It's might run out of room. Plus, we got a 1/2 acceleration in the y direction times delta t squared. I just got there. The last one, this is velocity in the y direction final squared equals velocity in the y direction initial squared plus 2 times acceleration in the y direction times not time but displacement in the y direction delta y. So those are the equations. All right, so these are the tools I will have available to try to work some things out. Now I go down here, and this large space is for working stuff out. It says decide which direction contains enough information. Enough information means we need 2 values for x or 3 values for y. Well, looking at what we have, it looks like I have 2 values for x, but this one doesn't count. That doesn't help me, because acceleration doesn't show up in any of those equations in the x direction. Well, I mean, never mind that one. That one's kind of like just there. Acceleration's not in either one of these, so that number doesn't help me. I have 1 value here. I can't start there. So if I have 3 values in the y direction, 1, 2, and I do have 3. Then I can find something in the y direction. I find the time. So what equation will I pick? Well, I need an equation with a t in it. I can pick this one or this one. No t in that one. And it turns out, let's see, do I know the final velocity in the y direction? No, I don't. So I know the initial, 0. So that's an unknown, and the t is an unknown. 2 unknowns in that first equation, can't pick that one. I'm going to have to pick this middle equation. So it's going to start with this. Initial times delta t plus 1/2 acceleration in the y direction times delta t squared. That's a 2. I swear, I promise. I gotta find the time. Okay. And it looks like, oh man, I've got delta t in 2 different places. This one even has an exponent on it. It's actually going to get easier. With this type of situation where it's a horizontal launch, that business right there is 0. So initial velocity in the y direction is 0. What's awesome about that is anything, no matter how much time there was, times 0, the whole thing goes away. All right. And that does actually help tremendously. 1/2 acceleration in y direction, delta t squared. Okay. And I got to solve this equation for delta t. Do I undo the exponent first? No. You undo these 2 things. These are getting multiplied to delta t squared. I have to divide. Move them over to the other side. Like that. And over here, cancel, cancel. Okay, I'm going to rewrite it to clean it up. Delta t squared. I'm not done. You recognize that. I haven't changed anything. I'm just rewriting it nice and clean. And now I got to take care of that exponent. Take the square root of both sides. Okay. And that gets rid of that exponent right there. So, great big radical. Not really. This is how I'm going to find the time. All right, and now, I got to plug some numbers in. Delta y, that was a negative number. Uh-oh, am I headed for trouble because I have that negative numbers under a radical? Is that going to cause issues? Watch this. What's the acceleration in the y direction? Negative g, so negative 9.8. It looks like the minus signs are going to cancel out. Yeah. So that's cool. In fact, that's kind of a sigh of relief moment because you should never have a negative under a radical for high school physics. Not really. Oh man, calculator time. 100 divided by 1/2 and divided by 9.8. And finally take the square root. Looks like I got 11.95. I'm going to round that to 12.0. Okay, found the time. But that wasn't the question. So 12.0 seconds, right? Cool fact about projectile motion. The time is the same for both x and y directions. I mean, it's only in the air for the amount of time that it is. So that's when it stops doing the y thing and when it stops doing the x thing. Well, now, all right, guess what? I've got the delta t, and I've got the velocity in the x direction. I'm going to use this equation to find that range. It's one last easy step. Velocity in the x times delta t. Velocity in the x was 6 meters per second. Time was 12.0 seconds. And the astute among you are looking at those units going, wait a minute, that's going to make meters per second squared. And then the more astute among you are going to be like, no, it isn't, because the seconds here cancels the seconds there. And 6 times 12, 72. That's the range, ladies and gentlemen. We did it. That is how far away from the base of the cliff. Away from the base of the cliff, right? That's the range right there, away from the base of the cliff. That's how far it lands. So this kid, this middle schooler, kicking that ball straight off the cliff, gets that thing 72 meters away from the base of the cliff by the time it lands. Bye.